Hi, I'm William, and this is going to be quantum lower bounds for approximate counting via Laurent polynomials. And this is based on joint work with Scott Aronson, Robin Cathari, and Justin Thaler. So to summarize this work in one slide, we introduced new quantum lower bound techniques for two extensions of the quantum query model that involve trusted states and untrusted states. We use these techniques to tightly characterize the complexity of the approximate counting problem, which I'll say a little bit more about what this is later. And in both settings, in both the trusted and untrusted setting, our lower bounds make essential use of Laurent polynomials. And if you've never heard of Laurent polynomials, these are basically just polynomials that can have both positive and negative exponents. So this is like a Laurent polynomial that has positive degree 3 and negative degree 2. So to say a little bit more, as I mentioned, we work in a generalization of the quantum query model. But first, just what is quantum query complexity? Well, the idea is you have some unknown input to a known function. So f is known, and you have an n-bit input x that is unknown, and you want to compute f using as few queries to the input as possible. So queries just means you get to ask for individual bits of x, what is that bit of x? And you want to compute f using as few queries to x as possible. And the quantum generalization of this is this oracle here that lets you make queries in superposition. And you just want to compute f with bounded errors. So let's say probability at least 2/3 of being right. And for the purposes of this talk, we're going to hope for algorithms that make a polylogarithmic an n number of queries. And the justification for this is that there's always the trivial algorithm that just makes n queries to the input. And once you've queried the entire input, you know with no additional queries what f is. So we're usually going to hope for something that does like substantially better than that. And in this case, substantially better is going to mean polylog n. And this is a very well-studied model. Most quantum algorithms can be formulated as algorithms in the query model, let's say. So the approximate counting problem is also a very well-studied problem, and actually was one of the first problems that we sort of understood well in the quantum query complexity setting. And the problem is just this. You have some unknown set S, and you want to decide whether S is large or small, where here large means has size at least 2W, and small means has size at most W. And it's a subset of this universe of n possible elements. And in the query model, the way we're going to access S is via membership queries. This is sort of the simplest way you can imagine formulating approximate counting as a query problem. And another way of saying it is that you get to make queries to the characteristic string of X. So this just tells you is the ith element in S. And these n and w parameters are kind of going to float around throughout this talk. So it'll be good to keep in mind what these are. And as I said, this was something that we understood pretty early on in quantum query complexity. We know that approximate counting requires root n over w quantum queries, basically. And pretty much both the upper bound and the lower bound are just generalizations of Grover's algorithm, or for the case of the lower bound, it's sort of a generalization of the lower bound for Grover's algorithm. And I really want to emphasize that this is a simple problem and a problem that we understand really well. And perhaps the reason why we understand problems like this so well is that we have good lower bound techniques. Between the polynomial method and the adversary method, which are two lower bound techniques for quantum query complexity, we usually know at least a rough idea of what to expect for the quantum query complexity of some problem. Like at minimum, we pretty much know whether we can expect like an exponential speed up for a quantum query algorithm over the best possible randomized algorithm. So this is generally a success story in the field. On the other hand, in this work, we ask what happens if you augment these query algorithms with access to a quantum state. So we're thinking of quantum states as an additional resource that maybe makes problems easier. And there are two sort of natural models to consider in this case. One is this untrusted setting. This is the quantum Merlin-Arthur setting, also the quantum analog of NP, where you have some short proof, but maybe an untrusted proof of the thing you're trying to compute. But there's also like another interesting setting to consider is where you have some trusted state. Maybe you have some known resource state that some algorithm or subroutine produces, or you just have it lying around and you want to know, does that state help you with query complexity? And in both of these settings, we sort of have embarrassingly few techniques. And this is just because, you know, these lower bound techniques are no longer valid. Once you give your algorithms additional resources, these lower bounds don't hold. So this sort of raises the question, you know, how helpful are quantum states as a resource, and what lower bound techniques do we have for these? And as I mentioned in this talk, we're going to study these questions for approximate counting, and we will actually see that the approximate counting problem itself is kind of well motivated by the questions, by the settings we're considering. So as I mentioned, we sort of have two results. There's this quantum Merlin-Arthur setting, and there's like this trusted setting. So I'll first talk about the untrusted setting. And the way we model QMA protocols in the query complexity setting is, well, there's two players. There's Merlin, who's this all-powerful prover, who knows the input x and claims something about x, claims that f of x equals 1. And there's Arthur, who's this skeptical but computationally bounded verifier who gets m qubits from Merlin and has to decide whether f of x equals 1 using at most t quantum queries to x. So this m and t sort of limit how much power Arthur has. And we'll just call this a QMA MT protocol. And already you can see how this might be useful for approximate counting. For example, you know, Merlin can send over maybe some of the items in S, and then Arthur can verify that those things are really in S using the queries. And so he can, you know, become convinced that yes, those things really are in S. Okay, so how do we prove lower bounds for QMA query complexity? Well, it turns out that essentially the only general lower bound technique we have for QMA is through this measure that's called SBQP. And I won't go into too much detail about what this is, but this is basically like BQP, except where the completeness and soundness parameters are 2 alpha and alpha instead of 2/3 and 1/3 for this alpha that the algorithm can choose in advance. And in particular, this alpha can be exponentially small, which is what gives these SBQP algorithms their power. And the connection between QMA protocols and SBQP algorithms is very simple. If you have a QMA MT protocol, there's an SBQP algorithm that makes roughly m times t queries. Now, this is a problem because for the approximate counting problem, the SBQP complexity of approximate counting is 1. Indeed, one way to describe what this SBQP measure captures is it is precisely the ability to do quantum approximate counting. And for our approximate counting problem, it suffices to just imagine an algorithm that guesses a random element in the set and checks to see if it's in the set or not. And if the set is large compared to the universe, then you know, it'll accept with probability 2 alpha. If it's small, it'll accept with probability at most alpha. So if we hope to prove like any non-trivial lower bound for approximate counting, we're going to have to do something a little bit more clever. But this also raises the question, what is the QMA complexity of approximate counting? And so again, recall there's this set S that Arthur gets to make queries to, and Merlin is trying to convince Arthur that the set is large. And Arthur's promised that either the set is large or it's small. And for these sorts of problems, there are always two obvious protocols. There's the one where Arthur does all the work. So in this case, Arthur just ignores Merlin and solves the problem using the best quantum query algorithm. But there's also the one where basically Merlin does all the work. And in this case, what that means is Merlin sends over 2 W elements of S. That's enough to convince Arthur that it's large. But really, you know, Arthur only has to check that like W plus 1 of them are marked because he's promised the set has size at most W or at least 2W. So he can verify that W plus 1 of the things that Merlin sent are marked using just like a constant number of queries by just randomly checking the things that Merlin sent. So in this talk, well, in this work, we show that these are basically optimal. Any QMA MT protocol for approximate counting, either the witness size needs to be basically as large as the set whose size you're trying to estimate, or Arthur needs to make enough queries to just solve the problem on his own. I will mention that, well, first off, notice that like unless W is really small or really big, this is not polylogarithmic in N. Like for example, if you choose W as like cube root of N, then both M and T are going to be cube root of N. I'll also mention that I think before this work, there was essentially no non-trivial lower bound known for this. Maybe like constant was known, but I don't think we even knew anything better than like polylogarithmic. An immediate corollary of this is a new oracle separation, which I won't really say more about, but basically this SBP measure is a classical approximate counting class. And so by showing that approximate counting is hard for QMA, it's sort of no surprise that we immediately get this new oracle separation. Okay, so how do we prove these lower bounds? Well, we have to get around this SBQP barrier somehow, and the key idea is to actually use a structural property of QMA. And this is an idea of Thomas Watson. So the structural property we exploit is that QMA is closed under intersection. And what does that mean? Suppose our function f has an efficient QMA protocol, then so does the and of two copies of f on separate inputs. So we have two inputs now, x and y, and we want to know is f of x and f of y true? And the reason why this also has an efficient QMA protocol is just Merlin sends copies for both, he sends witnesses for both copies, for both inputs to the function, and then Arthur checks both. So this gives us a new way to try to prove QMA lower bounds, which I will outline here. So suppose for a contradiction that approximate counting has an efficient QMA protocol. By the reasoning here, the and of two copies of approximate counting has an efficient QMA protocol. By the reasoning on the previous slide involving the Marriott-Watrous amplification, the and of two copies of approximate counting has an efficient SBQP algorithm. So if we can show that the and of two copies of approximate counting does not have an efficient SBQP algorithm, then we will have a contradiction. So this last step is what we're going to prove. There's no efficient SBQP algorithm for and of approximate counting. So how do we do this? Excuse me. So by completely standard arguments involving the polynomial method and symmetrization, you can actually lower bound this SBQP measure by the minimum degree of a polynomial that satisfies certain properties. And again, I won't really say too much about how this works, how you get to this polynomial, but I will say what this polynomial is. And what we need is a bivariate polynomial that has this behavior, where on this light gray region, it's large, and on these dark gray regions, it's close to 0, or let's just say, between 0 and 1, and here it has to be like at least 2. If you're wondering what these regions correspond to, well, these x and y variables correspond to the sizes of the inputs. So again, there's two inputs of approximate counting. So this x is like the size of the first input, this y is the second input. So this light gray region corresponds to the yes instances, where both sets are large, and these dark gray regions correspond to the no instances, where one of the sets is small. So how do we lower bound the degree of this bivariate thing? Well, I promised that this talk was going to involve Laurent polynomials, and so far this is just all ordinary polynomials. So maybe you can use that to guess where this is going. It turns out what we actually do is we pass a hyperbola through the plane and look at the polynomial's behavior restricted to this hyperbola. So formally, we look at p of x and then replace y by 4w squared over x. this is a multiple of 1 over x. So this ends up being a Laurent polynomial in x because we plug that in for y. It turns out we can also exploit some symmetry in this problem. There's this mirror symmetry along this axis, which actually lets us view this as a univariate polynomial in x plus 1 over x. And finally, this univariate polynomial you can lower bound using completely standard tools in approximation theory. And this is because what ends up happening is, so this hyperbola, it intersects this region here at this one point. So there's one point where it's large. And then it goes through this long region through these dark rectangles where it has to be close to 0. And that turns out to be enough to just lower bound its degree using completely standard techniques from approximation theory. There are a few more technical details in this proof. So for example, it turns out that really you only are guaranteed this behavior at the lattice points, so where x and y are both an integer. But it turns out that this is sort of really the only fundamentally new idea you need. You can deal with lattice points using some slightly more technical arguments. So that's basically everything I had to say about the QMA lower bound. So now I'm going to talk about a completely different setting where we look at approximate counting with access to certain trusted states. And the trusted states we're going to consider are quantum samples, or QSamples. And they're so called because it's the quantum analog of sampling. So we have the state ket S, and it's just the uniform superposition over things in S. So does this help you solve approximate counting? That's what we want to know. And clearly, this actually can be helpful in some cases. For example, if S is really small, even just regular samples are good for approximate counting. If there's only one element in S, then by just repeatedly sampling that element, you will very quickly see that's the only element in S, and you will very quickly see that S has size 1. So this is potentially useful, potentially more useful than just queries on its own. If we're going to throw this resource in, we also might as well throw in this other resource, which is this unitary operator RS, which is sort of a reflection about S, about ket S. And the reason it's a reflection is that it has the property that ket S is a -1 eigenstate, whereas all states that are orthogonal to ket S are +1 eigenstates. So does this help? And the reason why we throw this resource in is that it turns out if you have a unitary that prepares ket S, then in a completely black box way, you can turn that into this reflection oracle. So we might as well just throw that in too. So that raises the question, can you solve approximate counting efficiently using queries, reflections, and QSamples? Well, let's look at the upper bounds. So kind of similar to the quantum Merlin-Arthur setting, we can always just ignore the additional resource and just solve it using queries. So that gives us this algorithm. But there's a couple other algorithms. One is this algorithm that's not really new. It's based on collision finding. And the intuition for this is that suppose we had classical samples to S, then we could basically look for birthday collisions, so where we see the same element repeated multiple times in the samples. And by estimating the number of birthday collisions, we can infer an estimate of the size of S. This is just the quantum speedup you get from the collision algorithm, essentially, that turns that 1/2 exponent into a 1/3 exponent. And finally, there's an algorithm that's actually basically just this first algorithm in disguise, but where you replace the query oracle with this reflection oracle, and this turns out to work. This reflection oracle turns out to be sufficient to do amplitude amplification, which lets you do approximate counting using root and over W queries. So, are these optimal? Maybe you can guess where this is going. The answer is yes. In this work, we show either you need to make enough queries T to just solve the problem using queries alone, or you need to make enough queries to either QSamples or reflections We also show actually that for certain oracles that prepare QSamples or these reflections, this lower bound also holds. And for this R parameter, the lower bound just matches these upper bounds we have. So either we need like W to the 1/3 QSamples or reflections, or root n over W QSamples or reflections. And in particular, this is also not like polylogarithmic in n, unless, once again, well, if W is really small, then this algorithm is good. If W is really big, then these two algorithms are good. But if W is kind of in between, then neither of these algorithms is going to be too efficient. Okay. So how do we prove these lower bounds? Well, I'll actually kind of just jump right into the Laurent polynomials. So the standard polynomial method is, as I mentioned, it's a technique for proving lower bounds in query complexity. And it actually does give you a lower bound for approximate counting, for the quantum query complexity of approximate counting. And what it says is that the number of queries you need to solve approximate counting is lower bounded by the minimum degree of a real polynomial that behaves like this. Where it behaves like this means it has to be close to 0 between 0 and W, and close to 1 between 2W and N. Or more accurately, it has to have this behavior at the integer points in these two ranges. The Laurent polynomial method is a generalization of this that we introduce that shows that the number of queries, QSamples, and reflections you need to solve approximate counting is basically just the minimum degree of a Laurent polynomial that looks like this. And I put this degree in air quotes because, strictly speaking, there's sort of two parts to the degree of a Laurent polynomial that are relevant for our lower bound. There's like the positive degree and there's the negative degree. And both are important for lower bounding the two different resources, or I guess 3 different resources we consider. So why do Laurent polynomials show up? Well, I'm going to basically work through this for the case of just QSamples, and the proof for reflections is very similar. So I'm going to write this state, this QSampling state that we start with, like this, in terms of the characteristic string x. So recall that this xi is 1 if I is in the set, and it's 0 if I is not in the set. Because we have r copies of this state, every amplitude is basically going to be a product of r of these different xi's. So in other words, it's basically going to be a degree r polynomial in this input x. And it's going to be divided by this factor on the outside, this 1 over root s to the power of r, or another way of saying it is, the size of s to the power of r over 2. So the standard polynomial method, well, yeah, so from here on, actually, this is basically enough if you've seen the standard polynomial method before, because almost everything else is just applying the standard polynomial method. The standard polynomial method says that each time you make a query, you basically increase the degree of the polynomials and your amplitudes by 1. So as a result, after you make t queries, each amplitude is going to be a degree r plus t polynomial divided again by this factor, the size of s to the power of r over 2, because that kind of just floats around for the whole algorithm. To turn these amplitudes into probabilities, we square them, which turns our degree r plus t polynomial into degree 2r plus t, and divided by the size of s to the power of r now. And finally, by a symmetrization argument, you can actually just view this as a Laurent polynomial in the size of s. And so yeah, so really all that ends up happening is because of this 1 over root s factor that floats around, you get this negative degree in s, but otherwise it's like basically completely the same as the polynomial method. So how do we lower bound Laurent polynomial degree? Well, we actually have 2 different ways of lower bounding these. Only the second method is going to turn out to be quantitatively optimal, but I'll say a little bit about how they both work because they're both interesting. The first one is what we call an explosion argument. And the idea is you write the Laurent polynomial as the sum of an ordinary polynomial and sort of a purely negative degree polynomial. So just taking out all of the negative exponents. You argue that if both polynomials have low degree, then one of them has to have a large value somewhere. And the reason for this is that we know that their sum has, well, there has to be like a jump somewhere. And in particular, this jump implies that it has to have a large derivative somewhere. And using some completely black box tools from approximation theory is enough to tell you that one of these has a large value. But we also know that their sum is bounded, right? Because this polynomial represents a probability, their sum is between 0 and 1. So the other polynomial also has to be large somewhere. But you can actually basically iterate this argument to derive a contradiction, because it'll just force the other polynomial to be larger, which will force the other polynomial to be even larger, until you eventually get to a point where the polynomials are so large that they could not have existed in the first place. And this is just from the assumption that they have low degree. So you conclude that, well, they must not have had low degree. The other argument we give for proving lower bound is based on dual polynomials. And this is sort of more standard and in line with how many recent lower bounds on approximate degree have been proved. And the idea is you formulate this Laurent polynomial degree as a linear program. Then, to lower bound the degree necessary, it suffices to basically give a solution to the dual linear program. And the way we do that is by actually looking at two related linear programs. One is related to ordinary polynomial degree, and the other is related to the sort of purely negative degree polynomials. So in both of these cases, we're actually analyzing these Laurent polynomials by breaking it up into a positive degree and negative degree part. So you have these two solutions to these dual linear programs, and then it turns out you basically glue these together. And this is very hand-wavy. I can't really give it more justice given the time constraints of this talk. And this is also sort of the most technical part of the paper. But it turns out that this works, and this also just gives you a tight lower bound. So that's basically everything I had to say about how we prove these lower bounds. I'll wrap up with just a few open problems. I'll first point out that there are some open problems related to QMA query complexity that I think have been open for decades at this point. We don't know if there's an explicit function with linear QMA query complexity, meaning a function where Merlin basically doesn't help at all. And the reason for this is actually there's kind of another barrier in SBQP. If you look through carefully, you'll see that you really can't prove a stronger lower bound than like root n on the QMA complexity of some function if you go through SBQP. We also don't know if there's any possible separation between classical and quantum witnesses. This is sort of the famous QCMA versus QMA problem, where some people conjecture that there's like maybe an exponential separation between these two measures. But we don't even know if there's like a polynomial separation between the power of classical witnesses and quantum witnesses. So that's another very interesting open problem. Is there a real world setting where membership in QSamples are easy, but approximate counting is hard? This sort of models the trusted setting that we considered, and is there a real world setting that matches what we get in the query complexity setting? Are there other applications of Laurent polynomials? Well, it turns out I actually have one application which gives a simpler approximate degree lower bound for the and/or tree. But other than that, is there anything that sort of ties into this other question, which is there like a deep explanation for why Laurent polynomials show up in both this untrusted and trusted setting, right? Is there some underlying phenomenon that connects these two together, or, well, we don't know. So I think that's about everything I had to say. So that concludes the talk. I'm happy to answer any questions via email, but otherwise I will be around for the live talk where I'll also be happy to answer questions then. So thank you for coming to my talk.